But what we have here today for you is just a little bit of a midterm reflection. Because even though we're more than halfway through the year time-wise, we're exactly at the middle grade-wise. So what you're looking at here is half of your geometry grade, and I want you to understand how that grade is computed. So you can go into SIS and you can get your quarter one percentage. So just for example, let's say quarter one, I got an 84%. Then you can go into your quarter two grades and you can see your quarter 2%, and let's say I got an 88. So those percentages are what counts, not the letter grades. So now you can go ahead and you can look at your midterm percentage, and you got a score out of 40, and that is entered into your third quarter SIS progress report, and you can calculate the percentage. So let's say that I got a 34 out of 40. What I'm going to do with that score then is I'm going to go ahead and divide 34 by 40. Whoop. And I'm going to go ahead and look at how I did on my midterm, and that's going to be an 85%. So what we're going to do is understand that concept of weighting. Each quarter is worth 20% of your final grade. First quarter, second quarter, and your midterm and final together are worth 20%. But that midterm is half of that score, so that's why it gets a 0.1. So when we fill in your grades and what you got for each of those values, you can type in a mathematical equation to let you know with weighting where you stand in geometry right now. So it looks like this: 0.2 times 84. Calculator is going to do that calculation first. Then it's going to do 0.2 times 88 plus 0.1 times 85. And that is going to be a score out of 50 that represents how it's going for you in geometry right now. You can divide that by 50, and that's my score in geometry. It's my grade. A couple things about calculator fluency that's important for you to know. Your calculator does order of operations. So it goes through and works on all these multiplication problems first, and then it adds them together. If you get this answer and go right away to hitting the division sign, it'll carry that answer down. So if you wondered how I got ants there, is because I saved myself some time by not needing to type in 42.9 again. So the graphing calculator is filled with all kinds of fun, tricky things that we can do. And then I can know where I stand for the year. So if I'm feeling like I've got, that would round up to about an 86%. I'm feeling pretty good about that. Maybe I'm like rats. I was really hoping for an A. I have the exact same calculations happening again. So if I score higher, then that's going to increase that score. So if your goal is an A for the year, you know whether or not you've got some work to do. If your goal is a B, I want to maintain that, no problem. I don't think anybody's goal is a C. So we'll let you figure that out on yourself. So what we want you to also do is to take some time and reflect on your midterm preparation. We tried our best to give you every opportunity to look at and review, clean out your notebook, talk about notes, sample problems. So what I want is some feedback for you on how would you rate your level of preparation. Was it your best effort? Did you do your best, or nah, not really? Or anywhere in between? We kind of want some feedback on how you felt about what we did together. Did you feel like our class review and activities were helpful? If you have any comments about your rating, feel free to share them too. And number 3 is an interesting conversation because I want you to think about how well did your preparation and your score match. So if you did an awful lot of work and you got a great score, that's a perfect match. If you did an awful lot of work and you still didn't score that well, that's not a good match. Because for the kids that worked super hard and studied and did all the practice problems and checked their answers on Schoology and came in, if you did not score well on a midterm, we got an issue. We got to figure out what's going on. If you're a person who did not study, but you did great, okay. There's going to be time math catches up with you, but okay. If you did not study or prepare and your grade reflects it, that's actually a perfect match. And then what we want to know is what specifically worked well, what did you like, and you can also take this time to tell me what you didn't like too, because we'll let these comments influence what we do for when we go to prepare for the SOL and the final. So if you wanted more of something, if you wanted less of something, if you thought we're trying to balance whether or not we do too much homework, whether we, we're finding when we give kids the keys, they copy the homework and not a lot of learning happens, so that's never a good idea. So we want to know what specifically worked for you. So do me a favor, take some time, write at least 2 to 3 sentences. Give us something that we can learn from, reflect on. And then when you're finished, you can turn your paper over and get busy on reviewing, simplifying radicals. Yes? All right, so we're going to go ahead and start looking at simplifying radicals. And we're going to start with some review and some extension into that radical symbol, what it means, and how we end up simplifying things. So if you're still working on your reflection, I'll give you a couple more seconds to finish it up. And then we'll go ahead and jump into this. So this symbol here, it means to take the square root of, which means find 2 identical factors. This symbol here means to multiply a value times itself. Those 2 are opposites. They undo each other. So if I have the square root of something squared, my end game is just that thing. Now, if you want to see the math behind that, it goes like this. The square root of 23 times the square root of 23. When I'm multiplying radicals, if they match as far as their index goes, if they're the same kind of radical, I can put them under one radical sign together. So there I have my double factor that can come out of the radical sign, and that's how I end up with 23. If you're a person that wants to see it numerically, we can go ahead and say 23 times 23 is equal to 529. The square root of that answer back to 23. So the square root of something squared is that thing. So the moral of today's story is there's a long way and a short way to get to a lot of the math. Multiplication, for example, is a shortcut to repeated addition. If I spend $5 every day for 10 days, I'm not adding 5 10 times. In my head, I have my math facts. 5 times 10 is 50, so I spent $50. In mathematics, we're looking for shortcuts, and we can go back and prove those shortcuts, but we end up using them just because it's a faster, smarter, more efficient way of going about things. So when I'm looking at something like this one, for example, I know that this means 2 times the square root of 5 times 2 times the square root of 5. Now, if you look at this, how I wrote it, I removed the parentheses, and I just have 2 times the square root of 5 times the square 2 times the square root of 5. My commutative property of multiplication is the one that says you can switch things around when you're multiplying and still get the same answer. So I can call this 2 times the square root of 5 times the square root of 5. If I want to do it the long way, it's 4 times the square root of 5 times 5. Here's my double factor, or I could call that 25. It comes out of the radical sign. What I want you to see is that's 4 times 5, which is equal to 20. So looking at those properties lets me know how I can simplify these radicals. With your group, please work on 3 and 4 and 5. I want to hear you talking. Go. All right, so when we look at this one, our product property of radicals says if we are multiplying 2 radicals, just like we did up here, we can combine those multiplication problems. So the square root of 5 times the square root of 2 is the square root of 10. The square root of 3 squared is 3. This 2 is just a coefficient. So when I end up with 6 roots of 10, that 6 tells me how many roots of 10 I have. You have 6 of them. Any other questions you want to talk about? The only way to learn is if you ask. All right, next up comes these ones with the variables. Mr. Logan says, I don't like the ones with the variables. I'm like, I love the ones with the variables because you don't have to do those silly trees and break things down. This is A times, and this is 1, 2, 3, 4, 5, 6, 7 B's. So if I'm thinking about who can come out of the radical, this double factor comes out as 1. This double factor, I can make 3 groups of B. So B times B times B is B to the 3rd. Now what's interesting is I have 1 B that's left inside. So now I got to deal with my 80. That takes care of my variables. Now I'm going to start talking about my 80. Now I've seen a lot of you go ahead and break things down by 2 and 40 and 2 and 20 and 2 and 10 and 2 and 5. And then you go back and look for how many double factors there are. And that is a strategy for an 8th grade algebra student learning this for the first time. But we're beyond that. And we're going to use our number sense because these numbers behind Nora and Zoe are my best friends. Those are my perfect squares. Those are the ones that come out of the radical sign evenly. And if I'm looking at 80, I'm going to be thinking of 4s. Why 4? Because 4 is a friendly number with 80, first of all. And 4 is a perfect square. There it is on the wall right by Sumner. So I can go ahead and say 80 divided by 4 is going to give me, oh snap. So within 2 operations, not 1, 2, 3, 4 operations, in half of the time, I have my double factor and I have what's left. So when I go to break down 80, 4 comes out of the radical sign because I have a double factor, and 5 is left inside. So that simplifies down to 4ab cubed times the square root of 5b. So again, with that product property, when I have two radicals multiplied by each other, I'm not going to bother multiplying 45 and 60. Turn to your group and explain what I just did instead of multiplying 45 times 60. Go. So, number sense is described as having a good sense of numbers. And if you have good number sense naturally, congratulations, math gods have bestowed that upon you. If you don't have a good sense of numbers, get busy learning it, because it's easy to start thinking about numbers. When I look at 45, I see my best friend 9. I know my math facts. I'm looking for my perfect squares. I'm looking for values that are friendly with 9. So I see 9 and 5. As soon as I see that 5, I'm like, oh snap, 60 is divisible by 5, because I know my math facts. So once I know 5 goes into 60, I totally am looking at 12. Oh snap, 12 has 4 in it. So just by looking at the numbers, instead of multiplying these to a number that's way outside what I have stuck in my head, I can break down 45 into 9 and 5. I can break down 60 into 5 times 4 times 3. And what I set myself up for was understanding that 9 is a perfect square. Square root of 9 is 3. Here's a double factor. That can come out of the radical as 1. Here's a perfect square. Square root of 4 is 2. And then I have root 3. 15 times 2 is 30. So I have 30 roots of 3. If I ever wanted to test to see if I did it right, put 30 back in. 30 times 30 times 3. That puts me up to here. Hopefully 45 times 60 is that same value, so I know I did it right. We want to spin the numbers around in our head. We want them to make sense to us, and they want them to work for us. When I multiply radicals, I can put 2 and 8 under the same radical sign. Notice how I wrote 8. 8's not a perfect square, but 4 is, and here I have these two 2's. So my 3 is a coefficient on the outside, square root of 4 is 2, and here's my double factors. Guess what? There's nothing left inside the radical, so I don't have to write it. 3 times 2 times 2 is 12. That answer simplifies cleanly. If your answer simplifies cleanly, you just write it without a radical sign. So you look at numbers 1 through 8 and tell your group mates which ones you already knew how to do and what were new to you. On your mark, set, go. Here's something that I think is new to you. It's called rationalizing your denominators. Here's the deal. There is a current argument in the mathematics community. Somewhere in the ivory towers of mathematical knowledge, people are arguing about whether or not we still need to rationalize all denominators. Years and years and years ago, the thought was, if a fraction is a part to whole and I can't conceptualize my whole because it's an irrational number, can't have that. I'll say that one more time. Every time I try to take the square root of a number that's not a perfect square, I end up with an irrational number. So if every rational number represents a part compared to a whole, and I can't conceptualize that whole as a value, how can I say that that's a rational number if it's out of a number that's an irrational number. Do you understand the conundrum? So mathematicians scratched their heads and they thought about it and they're like, I know what we can do. Because the square root of something squared is that thing, let's use that to manipulate our values. And all of his friends were like, you're so smart, I wish I'd thought of that. So here's what we're going to do. This guy says, if this guy is just multiplied by another root 3, I would get rid of the radical because the square root of 3 times the square root of 3 is 3. So then his friends are like, dude, you can't do that. You can't just multiply by whatever you want. You just change the value of that number. He's like, oh, good point. I'm going to use my multiplicative identity because if I multiply anything by 1, it's the same value. So anything times 1 is itself. So this is like mathematics at its best. I'm going to get my way because I'm a spoiled brat. I'm going to make the math work for me. So now what I've done is I have 4 times the square root of 3. Root 3 times root 3 is 3. So now I've made the math gods happy by putting a whole number in the denominator. And I still have that radical in the numerator, but nobody's upset about that. That's the process called, and again, we're not creative when we name things in mathematics. What did you do? I just rationalized the denominator. Hey, let's call it that. It says creative is the Zach Brown Band. Who are you? I'm Zach Brown. This is my band, the Zach Brown Band. So when we have 4 roots of 3 over 3, I've just rationalized my denominator. Hey, with your group mates, go rationalize these denominators. And Marcus said, go. All right, so take a look at mine. And you're like, wait, what? So I definitely went ahead and I rationalized this denominator. This guy needs another root 2, so I gave it to him. Anything over itself is equal to 1. So I did not change the value of the number. Root 2 times root 2 is 2. 8 times root 2 is 8 roots of 2. But notice this is a fraction that I can simplify, and I absolutely have to do that. So the rules say you have to simplify every chance you get, which is exactly what I did. So this one, you're like, what the heck? Where's your work? And this is going to introduce to you my quotient property of radicals. If you have 2 radicals that match, they're the same type of radical, square root, cube root, fourth root, these are both square roots, I can go ahead and I can put them under one radical sign and I can simplify. 10 divided by 2 is 5, so then I get the square root of 5. That's my answer. You're like, that's cheating. You didn't tell us we could do that. I especially love doing this when my numbers are friendly. Because when I get the square root of 9, that ends up being something that I can simplify further. This next unit that we're doing has us doing an awful lot of simplifying radicals. So no more excuses. You've been taught it a number of times. So we're going to make sure that you know how to do it. All right. Especially when we go to give you problems like these. Go ahead.
Wait, I'm still a little bit confused about number 10. Why did you divide, yeah, I'm still confused about number 10.
So I have this radical in the denominator that I don't want.
Yeah.
So I'm going to multiply by itself to make that radical go away. And then I'm going to make my fraction be the same thing over the same thing because it's 1. You with me so far?
Yeah, I get that.
So 8 times the square root of 2 is 8 root 2. Square root of 2 times the square root of 2 is 2.
Yeah, but why are you dividing
These-
the radical by 2?
Because this is 8 times 2 divided by 2. So that would be the same. Imagine if I had 8 times x divided by 2. Because this is multiplication, I don't have to distribute. There's no plus or minus sign. It's just factors that can simplify. See it?
Yeah.
Okay. All right, so when we're coming down here, we're going to have to deal with these fractions or with these radicals. And if I want to classify the triangle, my first step is I want to be like, wait, before I classify, I want to know, is it a triangle? And if I'm checking to see if it's a triangle, the sum of the two smaller sides have to be bigger than the third side. That's not Pythagoras, because Pythagoras is the one that has all the squares. So that's not Pythagoras. Pythagoras is the one where I have a squared plus b squared and c squared. This is just, is it a triangle? That's all I want to know. So your first order of business is deciding which of these three values is the largest. And that's your hypotenuse, or your longest side, and you have to make sure that the smaller two are bigger than it. After you determine, yes, it is a triangle, then you have to compare c squared to a squared plus b squared. And that's where you're like, okay, if it's equal, it's right. If c squared is bigger, it's obtuse. If c squared is smaller, then it's acute. With your partners, go, classify the triangles.
This one.
Do we agree?
Yes.
Do we agree?
Yeah.
So for this example, this is my largest side. This is my largest side. And this is my largest side. Hey, a trick that one of my past students taught me, I was having them enter into the calculator to see which one was the biggest. And the student said to me, why don't you just put it back in the radical? I'm like, go on. He's like, if you want to know what's bigger, put 2 back in. Because it was 4 before it came out. So this is 5 times the square root of 20 times the square root of 10. And you could even have this as 5 is the square root of 25, which means that this one is actually 5 is bigger. So when we're comparing this one, put him back in. 4 times 2 is 8, so the square root of 8 is bigger. Put him back in. This is the square root of 27 compared to the square root of 9 compared to the square root of 3. So if you don't have a calculator and you have those radicals, putting that coefficient back in by squaring it, it came out by taking the square root of it, put it back in. Go ahead, Trina.
I thought when it says classify the triangle, that would be classified by itself. Why is it that way?
Usually we classify it by angles and sides. All of them are scalene because none of them are repeats.
Yeah.
So we care more about the angles at this point. All right. Last thing on our little review
Wait.
goes like this. Are we okay?
Yeah.
Last thing, just like we can square both sides of an equation, we can take the square root of both sides of an equation. So when we're solving with a quadratic in it,
See,
Like you're doing the same thing.
it's just you don't get X.
Sorry.
did you figure it out?
Yeah,
Yes.
we got it.
Rock on. Subtracting 3 from both sides, I get the square root of x is equal to 10. Our x squared is equal to 10. I take the square root of each side, and I get x is equal to plus or minus the square root of 10. I don't need to simplify that anymore. Let's talk about that plus or minus. Whenever I have a value squared, I have the potential of losing that negative, which is disastrous. We can't do. So what we end up doing is anytime that you are solving for an x squared and you draw the square root sign of both sides of an equation, you have to think that if I had a negative root 10 squared, then I would still get that same value. So we need to make sure that we understand that we might lose a solution. Your Algebra 2 teachers will love you if you remember the plus or minus. Geometry teachers, not so much. Most of the time what we're solving for is a distance. A distance can't be negative. So if we're solving unattached problems like these that are not grounded in anything, you have to include the plus minus. If you're solving for the distance of a leg of a triangle, no negative distances. But these are kind of fun to play with because when you add 4 to each side, you get x squared is equal to 128. So then when you take the square root of each side, x is equal to plus or minus. When I think about 128, I know a 4 goes in 32 times, and then I have a 4 times an 8, and a 4 times a 2. So comes out as a 4, this comes out as a 2. 4 times 2 is 8, so x is equal to plus or minus 8 roots of 2. If I want to check and see if I did my math right, I can do 8 times 8 times 2, and that matches that 128. So that's a quick double check that you did it right. All right, here I'm going to divide by 6 first because I want to isolate my x squared. So if I have 294 divide by 6, hello, perfect square. When I take the square root, x is equal to plus or minus 7. I could put a positive 7 into this. I could put a negative 7 into this. And that squaring is going to square away that negative. So they're both possible solutions. Remember, when you're solving for x, you're looking for all the possible values that will make that equation true. All right. I'm going to add my 61 to each side to combine like terms. So 5x squared is equal to 125. I'm going to divide by 5. My x squared is equal to 25. I'm going to take the square root of each side. So my x is going to be equal to plus or minus 5. Solving equations with a square are kind of fun once you get the hang of it. All right. So what I want you to do right now is once you finish, I want the reflections in my inbox. So let's have quadrant 1, friends. Make sure everybody's name is on the paper and turn the reflections into my inbox, please. Quadrant 2, check and make sure that there's a pair of scissors for each of your friends. If there's not, go to the back and get one. Everybody needs their own pair of scissors.
Don't play with scissors, kids.
you all have, let's quickly talk about our next unit. Here we are, right triangles. Today's topic is similarity in right triangles. And the version of the assignment sheet that's online will have this live link. So if you want to watch another version of the activity we're about to do today, you can do that there. Next week, we're going to start talking about special right triangles. And it's one of those things where once somebody explains it to you, you're like, oh, that's pretty cool. I didn't know that was true. But we need you to pay attention because it's something that I'm pretty sure is going to be completely new for all of you. We'll have a quick quiz on lessons 1 and 2, a review of the Pythagorean theorem. And then we're going to jump into one of my favorite topics to teach, which is trigonometry. And we're going to talk about trig ratios. Trigonometry is the study of triangles and their relationship and right triangles. It's very cool. You're going to love it. We're going to solve problems of angles of elevation and depression. Have another quick quiz and then a unit test. My plan is to return your Unit 6 tests next week. I still got a bunch of people waiting to take it. If your name is on my board, I need you to make sure you make up. Believe it or not, I still have kids that need to make up the 5B quest. The Unit 6 test. And then, of course, our midterm. Wednesdays and Thursdays after school is when we are good to go. Yeah. Questions on, and again, if we're talking about something and you're like, oh, I know what that is, don't forget that on the back of the sheet are pictures and diagrams that go with our topics that not only get you some extra credit points, but also help you organize your thinking and help you studying. And I saw somebody organize their notebook where they had, I want to say, was it you, Sully, where you had all of your assignment sheets with all the notes stapled together? Was that you? Yeah, so that was a pretty good strategy for him, keeping all of his content together. I loved it. All right, here we go. Some right triangle fun. Would you please take your right triangle? Would you please, you're like, that's not a right triangle. I'm like, yes, it is. There's 2 of them. Do you see the 2? Would you please, and I want you to do your best. I want you to do your best first grade cutting. So, cutting is a kindergarten skill. You can't leave kindergarten without being able to cut. So if you need to kind of finagle the line a little bit to go from diagonal corner to corner along the diagonal, go ahead and do that. But we want you to do your best first grade cutting skills. So that you can take your rectangle, and from that rectangle, you can create 2 congruent right angles. I'm hoping that you are a pretty good cutter and that you were able to get them to be as congruent as you could. Pretty good, right? All right. Oh, okay. So now what I want you to do is I want you to take one of your 2 triangles. There we go. Take one of your 2 triangles and swap it with a person so that you have one of another color. So within your group, swap. So that you have 2 triangles of a different color. Theoretically, your triangle should be congruent. You should be able to lay one triangle right on top of the other. You may have to flip it, turn it. But theoretically, you have 2 right triangles. Okay. Your next step Your next step is to take one of your two right triangles and you're going to turn it around so that this right angle is at the top. And what you're going to be doing is folding along the altitude. Now the best way to find the altitude is to fold straight here and make it so that your line goes right up into your angle. So it is a little delicate, and you do want to try to get the best fold that you can so that this is a good fold here and that this goes up through your vertex. And when you do that, you're going to again take your scissors and you're going to cut along that altitude. You want me to do it with one?
That has like the right angle addition. I'm like, oh, you know what? To me, because we just talked about radicals, to me it's additional.
So then you're going to again swap. You're going to again swap one of your triangles with somebody else so that you wind up with triangles of 3 different colors. A small and a medium and a large triangle of 3 different colors. Cut it along there.
Okay, now.
Along this edge.
You should have told us to do it of our own color. Because now we have 2 pinks.
So once you do that, swap with your group mates so that everybody has 3 triangles of a different color. Everybody good?
Similar, just here, like mark one of them.
So you got a fold and cut.
Me and Kylie are on pink. Love to see
Yeah,
it.
just take it.
We failed.
They both cut the same.
Yay! Trade.
That's easy fix. Anybody else's group need a quick swap? You need 3 triangles of a different color. Everybody good? Okay, here's a really cool thing. What I want you to do is identify which of your angles are the right angles. So draw a box and do me a favor, draw a box on both sides of that right angle. Find your right angle and label it.
Well,
And then I'll go ahead and go one step further and name your triangles big. Name your triangle medium. And name your triangle small.
bigs and small.
Once you name them big, medium, and small, go ahead and gather them in your right angle, and you will not be surprised at all that you happen to have 3 similar triangles. We call this a physical proof. In the first part of your notes today, it talks about when an altitude is drawn to the hypotenuse of a right triangle, it divides the triangle into 3 similar triangles, and you can prove that right now with angle similarity.
My angles aren't equal, they're slightly different.
So you can have big, medium, and small, and you want to make sure you have them lined up so that they all look like similar triangles. And you can prove that. Slide them around and match up the angles. How cool is that? You just did a physical proof. of our first theorem today. Now here's the deal. Start playing with your triangles. See if you can take your big and your medium and your small and rebuild your original. Can you rebuild your original?
Oh, yeah. There we go. Oh, I got it, guys. I did it. You like reverse them. It's confused.
You do need to flip and turn and spin. It is definitely hard. And some of us have a greater aptitude for that than others. But you want to see if you can put the puzzle back together again.
Why am I struggling so much?
Nope.
Okay? Sumner, can you do this puzzle?
Yeah.
Okay. And then the next puzzle,
This is so obvious and I'm having so much trouble with it.
Oh, now we're gonna rebuild the main thing.
the next puzzle is, can you put them together?
Because that was what's going on?
Big is equal to small plus medium. You want help?
No,
You had it. You're
I
like
had it,
there.
and I messed
You're
it
there.
up.
It's like the Wordle. I don't want help.
yeah.
I'm gonna figure it out.
Everyone has been playing
There.
Have you not?
I had it. I just didn't see it right.
It's late. You must join the Wordle ways.
So you notice that there's a lot of flipping around and whatnot.
Why so mean?
Kind of fun with
Nice.
triangles, for sure. All right, so on today's notes, let's talk about what we've already done. Ready? Take a triangle, or take a rectangle, check. We already got that done. Cut along a diagonal, check, we got that done. Fold and cut along the altitude to the hypotenuse. Make sure you understand that here's our hypotenuse. Here's our hypotenuse, and here is an altitude to the hypotenuse, and that is where we cut along that triangle. Now we have three similar triangles, a small, medium, and a large. And we proved their similarity by angle similarity, so we're good. Okay, now what I want you to do is I want you to name or arrange your big and your medium and your small triangle in a row, and I want you to label them with R, X, Q, S, Y, and T, like you see here on my diagram. So if you take your large triangle, on both sides, I want you to label the long leg R. I want you to label the hypotenuse X and the short leg Q. For your medium triangle, I want you to label your long leg S, hypotenuse R, short leg Y. For your small triangle, I want you to label small side, short side T, long leg Y, hypotenuse Q, and if it's helpful to you, you can give yourself your right angles. So now every single one of these proportions here can be solved using these two triangles, but you got to be careful about which are, because there are some repeats. There are some repeats. So when I talk about comparing Q to R or Q to R, I want to try to get in this Y. So I need to be using Q to R is equal to what to to y. Q to r, hypotenuse to hypotenuse, is equal to t to y. So you might have to look through a couple different triangles to make it work. With your group, go ahead and talk about your triangles, talk about proportions, and match up what letters go where. Go. Our group over here is starting to see the connection between why there's double letters. Do you see that y is serving a double duty? Y is both the long leg of the small triangle and the short leg of the medium triangle. Do you see how y has two jobs? So you ended up with y being a geometric mean in this ratio here. Because that y is the geometric mean between these two pieces here. Kind of cool, right? All right, let's talk about Q. Do you see how your Q's match up? Q is also doing double duty. Q is the short leg of the big triangle and the hypotenuse of the small triangle. Q does double duty here in this ratio. Which is our other side that does double duty? R. Sure. So here, R does double duty. Because R is both the long leg of the big triangle and the hypotenuse of the medium triangle. We can even call this Q a mean because we can use our properties of proportions and flip him around a little bit too. So every single thing we're going to be learning today is a shortcut to what works because of similar triangles. So a lot of textbooks put this lesson in with similar triangles and they make the kids understand it. I like it as a part of right triangles because it's all a part of our shortcuts that we're going to learn and some cool properties of similarity among right triangles. All right, so we'll put this aside and we'll go jump into the notes and we ask ourselves, what special patterns or relationships do you notice? And I want to make sure that somewhere in your notes you have written down that y serves a double duty. Q serves a double duty, as does R. And I want you to write down what they each are. R is the long leg of my big triangle. It's my hypotenuse of my medium triangle. Q is my short leg of my big triangle. Q is my hypotenuse of my small triangle. And then we can talk about Y. Y is my short leg of my medium triangle. And it's my long leg of my small triangle. So because in these similar right triangles, each of these legs and this altitude serve a double duty, they're going to give us all kinds of geometric mean theorems. First things first, if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and similar to each other. Basically, we wind up with three similar triangles. Hey, here's my hint for you. If you're ever looking at a picture like this, it's kind of a lousy picture because it doesn't necessarily make it easy for me to see what is my long and short legs. So take the time to sketch a more exaggerated version, because if you do that, then it'll be easier for you to see which is long leg, short leg of each of the triangles. That's just my advice. Makes it easier for sure. All right, here comes our fun geometric theme, our geometric mean theorem. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. We don't necessarily need to worry about that. We just need to know that this is the story that happens for both of these relationships. I have a right triangle, I have an altitude, my hypotenuse is divided into two segments. To make this match your triangles that you're playing with, go ahead and give those same values, because this is T and this is S and this is Y. Here's Q and here's R. This first conversation is about Y. Y is going to be the geometric mean between S and T. Some kids prefer to see it this way. Y is the geometric mean between these two sides. If you look at what it is I'm comparing, I am comparing short leg to short leg, long leg to long leg. Short leg to short leg, long leg to long leg, depending on when we're looking at the triangle. So when I know about my segment BD and AD, they are both my pieces of my hypotenuse, and CD is going to be my altitude that serves as that geometric mean. Sometimes we remember this one by doing a loop-de-loop. That Y is included in both of the proportions in the geometric mean position. Okay. Our next conversations, again, take the time to label your triangle so that you can use your models that we spent so much time cutting and labeling and building. Except for this time, you're going to need to make sure that you include X, because X is the hypotenuse of the big triangle. This one tells us that CB is our geometric mean. That's going to be Q. Q is our geometric mean between this whole length and this side that it's touching. So what we end up saying is Q is a geometric mean between the piece that it's touching and the whole. This Q is the geometric mean between this piece that it's touching and this whole side here. I'm comparing short leg, hypotenuse, hypotenuse. Short leg, hypotenuse, hypotenuse. Of similar right triangles. If I'm talking about R, I know that R is going to be the geometric mean this dB goes here. right? CB is a geometric mean between, yeah. R is going to be the geometric mean. Here's our AC, R, and here's our R. Between the piece that it's touching, that's AD. AD. The piece that it's touching, and this hole. So what I frequently wind up saying is that it's a geometric mean between the piece of the hypotenuse it is touching and the whole hypotenuse of my big triangle. And that goes with this one. Okay, so we're going to skip number 1 for now, and we're just going to jump down to 2 and 3 and look at these easier ones. Here's my x that I'm solving for. I have an altitude from the right triangle, from the right angle to the hypotenuse. This is my example of my loop-the-loop. So I know that x is my geometric mean between these two pieces of the hypotenuse. And here's why we spend all that time reviewing radicals. We don't need our plus or minus on this one because it's a distance of a part of a triangle, and that's not going to be negative. When we talk about this one, y is going to be my geometric mean. And this is a different kind of loop-de-loop because the piece that it's touching and the hole. Y is going to be the geometric mean between the piece that it's touching and that hole. And that hole, mind you, we have to add together those two pieces. So let's come up here and take a look at this one. When I want to solve for h, that's my job here. But if you notice, I have my hole, but I don't have either piece. So I'm going to have to use either this or this to find these two first. I'm going to go ahead and use 11 because I'd rather not deal with decimals. I know that 11 is the geometric mean between the piece that it's touching, we'll call that B, and my hole. So when I go ahead and use my calculator, I can have 11 times 11, 121. So 1 B times 11.96 is equal to 121. B is equal to 10. Once I know this value is 10.12, I can subtract it and get this value here for A and B. So this little piece here is 1.84, we'll call that A, and B is that. Now when I go to solve for H, And I'll come over here and I'll solve for h. H is the geometric mean. Here's my loop-de-loop. 1.84, 10.12, h squared. $18.62. When I'm dealing in a real world problem and I'm monkeying around with decimals and whatnot, I'm simplifying the radical is not realistic. So I'm okay with you using your calculator to round to the nearest hundredth. So that means that h is equal to 4.32. So first I had to find b, then I used subtraction to find a, and then I used both values to find h. So all of those formulas can work together. I just need to keep track of whether it's the piece and the altitude involved, or the short leg, long leg with the hypotenuse that's involved. Sound okay?